All right, welcome to the Explainer. Today, we're diving into what sounds like a really simple question. How do you measure the real distance between things when you're dealing with complex data? Well, it turns out the answer isn't just a straight line. It forces us to understand the hidden and kind of fascinating shape of the data itself. So, to get our heads around this, let's start with a puzzle that seems, well, pretty straightforward on the surface. Imagine you've got a handful of companies, and your job is to figure out which one is the most typical, the most average of the bunch. How would you even begin to do that? Let's get specific. Here's some real data for 4 companies, showing their sales, profits, and assets. You know, if you just eyeball these numbers, there's no obvious answer. C2 has the highest sales, but C3 has the most assets. We need a consistent way to measure how far each company is from the center of this group. Okay, so first things first, we have to figure out a way to measure this abstract distance. Let's start with the tool we all probably remember from school. This is the good old Euclidean distance. You can just think of it as a ruler for data. The logic seems simple enough. We calculate the average company by just averaging all the sales, profits, and assets. Then we use this formula to measure the straight line distance from that average point to each of our 4 companies. The one with the shortest distance must be the most average one. Seems logical, right? But, and this is a big but, this simple approach has a massive hidden flaw that can completely mislead us. The problem isn't the formula itself, it's the data we're feeding it. Just look at our features again. Sales are measured in the thousands, but profits are way down in the hundreds. When we plug these numbers into our simple ruler formula, the huge numbers from sales are going to totally drown out the smaller numbers from profits. A tiny change in sales will look way more important than a massive swing in profits. And that's the heart of the problem. Our distance calculation gets completely dominated by whatever feature just happens to have the biggest numbers. Our ruler stops being a fair comparison and becomes almost entirely about sales, totally ignoring what the other features are trying to tell us. So, how do we fix this mess? Well, we've got to find a way to get all our different measurements onto the same playing field. And in statistics, there's a perfect tool for that. It's called standardization. The process is actually pretty clever. First, you find the average for each feature, sales, profits, assets, all of them. Second, you measure how spread out each one is, which is its standard deviation. And finally, you use those numbers to rescale every single data point. This makes everything unitless, so now they can all be compared fairly. Okay, great. Problem solved, right? We've fixed the scale issue, everything's fair and square, we can just use our trusty ruler, the Euclidean distance, on this new clean data and call it a day. Or can we? Yeah, unfortunately, there's another wrinkle. A much sneakier problem that standardization just doesn't touch. It's all about the hidden relationships between our different features. I mean, think about it for a second. It just makes sense, right? A company with huge sales probably also has a lot of assets. The two things are connected. When features tend to move together like this, it's called correlation. And that correlation fundamentally changes the shape of our data, warping the very space our ruler is trying to measure. To see this new shape, we need a special kind of map. And that map is the covariance matrix. It basically gives us the data's geometry. The numbers down the middle, the diagonal, tell us the spread of each feature. We've seen that. But the real magic is in the off-diagonal numbers. They captured the relationship, the covariance between any 2 features. So here's the crucial insight. Because our features are related, our data points don't form a nice round cloud. No way. They form a stretched out, tilted ellipse. And trying to use a simple ruler in a space that's tilted like that is like trying to measure a straight line in a funhouse mirror. You're going to get the wrong answer. We need a distance measure that understands the tilt. And that right there brings us to the hero of our story, a seriously powerful statistical tool that was designed to solve both of these problems at once, the problem of different scales and the problem of correlation. Meet the Mahalanobis distance. Now, I know the formula looks a little intimidating, but the idea behind it is just brilliant. It starts with a simple distance, but then, and this is the secret sauce, it adjusts that distance using the inverse of that covariance matrix we just talked about. That little s⁻⁻1 is what mathematically untilts the data ellipse back into a perfect circle right before it takes the measurement. First off, because it uses the covariance matrix, it automatically handles the different scales of our variables. It just innately understands that a 1-unit change in sales is a different beast than a 1-unit change in profits and adjusts for it. And second, this is its real superpower. It accounts for that tilt in the data. It essentially untwists the ellipse, measuring distance along the natural axes of the data cloud itself, not some arbitrary axes on a graph. What you get in the end is a true statistical distance. It tells you how many standard deviations a point is from the center, but it's a special kind of standard deviation, one that respects the data's unique correlated shape. It's a truly scale-free and correlation-aware metric. Okay, so let's take this incredible new tool and go all the way back to our original puzzle with the companies. Now we can see why understanding the shape of data is so critical to getting the right answer. And voila, here is our result. After we apply the Mahalanobis formula, we get a single, powerful number for each company. And this isn't just a simple distance. It's a true measure of how typical each one is because it's corrected for both scale and the hidden relationships in the data. The solution to our puzzle is now crystal clear. The company with the smallest Mahalanobis distance is our winner. It is, statistically speaking, the most average company of the group. By finally respecting the data's true shape, we found our answer. And believe me, this isn't just some neat academic trick. This exact concept is absolutely critical across industries. It's used in finance to spot unusual stocks, in medicine to flag abnormal patient data, and it's really the bedrock of outlier detection in machine learning. Anywhere you need to find the odd one out, this is the tool for the job. So the next time you look at a data set, don't just see rows and columns of numbers. Remember that data has a shape, a geometry, and by choosing the right tools to measure it, we can uncover insights that would otherwise remain completely hidden. It really makes you wonder, doesn't it? What other invisible structures are out there just waiting for the right ruler to be discovered?